All right. So this time let's look at problem 2.4. This one is about the transfer of thermal energy between two objects of different specific heats. So let's read the problem and then look at how we would go about solving this. So we're told that a mug is filled with 400 grams of tea, which has a specific heat of 4190 joules per kilogram degree Celsius that starts at 90 degrees Celsius. A 100-gram silver spoon with a specific heat of 240 joules per kilogram degree Celsius at 10 degrees is used to stir the tea slightly and left in the tea for a few minutes until they reach thermal equilibrium. Assume that no thermal energy is exchanged with surroundings during this process. So what we're told is the mass of the tea, the specific heat of the tea, the initial temperature of the tea, the mass of the silver is 100 grams, the initial temperature of the silver is 10 degrees Celsius, and we're told that they reach thermal equilibrium, which is a fancy way of just saying that their final temperature is going to be the same. So the final temperature of the tea is going to be the same as the final temperature of the silver. So let's draw our sketch. So we're going to have our initial state and our final state. So here is our cup. There is my spoon. We have the mass of the silver is 100 grams. The temperature of the silver is 10 degrees Celsius. We have the mass of the tea, 400 grams, and the initial temperature of the tea is 90 degrees Celsius. And then in our final state, they still have the same mass. So the mass of the silver is 100 grams. The mass of the tea is 400 grams. But they're in thermal equilibrium, so we know that there is just some final temperature, but we don't know what that is yet. So this is our initial state. Now, we want to draw an energy bar chart. Showing the change in energy for this system. And notice that I've given you a hint here in the problem. So label the changes in each object's internal energy with separate bars. Because if we're assuming that no thermal energy is exchanged with the surroundings, then the total energy of the system isn't changing. So if I were to just represent the total energy with individual bars, there would be nothing happening, and it wouldn't really be helpful to me. So what's happening in this problem in terms of the energy? Well, we start with no energy relatively. There's no heating from outside the system. There's no work from outside the system. And what's happening? Well, if they're going to reach thermal equilibrium, the spoon is going to warm up, which means the spoon is going to gain thermal or internal energy. In this problem, they're interchangeable. Let's say it's gaining 3 boxes of internal energy in the spoon. Well, where is that energy coming from? We were told that it's not coming from outside the systems, it's not coming from the surroundings. So it has to be getting that energy from the tea, which means that the tea has to be losing the same amount of internal energy. So this is why we're representing them with two separate bars, because if we just represented the total internal energy of the system change, those would cancel each other out and we'd have no bars. It wouldn't help us. So this tells us that the total energy change in the system is 0, is equal to the internal energy change of the spoon plus the internal energy change of the T. So we know this because all the energy the spoon gains comes from the T, not from anywhere else. So now we can solve for that final temperature. So from our bar chart, we know that 0 is equal to the change in the spoon's internal energy plus the change in the T's internal energy. And we also know that this change in internal energy is coming from a change in temperature, not a change in phase. So because delta U internal comes from a change in temperature, we can describe it with the equation that we learned in lab this week, with delta U internal is equal to mc delta T. So 0 is equal to m of the silver, c of the silver, delta T of the silver, plus mass of the T, specific heat of the T, change in temperature of the T. So now, all we need to do is plug our numbers in and solve. So I'm going to start all the way over here, make sure I've got enough space. So the mass of the silver was 100 grams times the specific heat was given as 240. Joules per kilogram degree Celsius. And I notice immediately that I've got a unit problem here because I've got grams and kilograms and I don't like that. So let me change the 100 grams into 0.1 kilograms. That way my units can cancel a little bit easier. Times change in temperature. Well, the change of anything, delta T is always going to be equal to the final minus the initial. That's just what it means to be the change. So the final is what we're looking for, minus the initial temperature of the spoon was 10 degrees Celsius, plus the mass of the T was 0.4 kilograms. The specific heat of the T was 4190. Joules per kilogram degree Celsius. And again, we're going to have the same thing. TF, final temperature, minus the initial temperature of 90 degrees. So just because I don't feel like writing those units every time, all of my kilograms will cancel out. And now 0.1 times 240 is 24. So I get 24 joules per degree Celsius times final temperature minus 240 joules per degree Celsius. That's just 0.1 times 240 times -10 is -240. Those cancel out, and I'm left with joules. Plus, and now I'm actually going to have to use a calculator. Future, I should pick numbers I can do in my head every time. 0.4 times 4190 is 1676 joules per degree Celsius times final temperature minus 0.4 times 4190 times -90. 150,840 joules. So I can get all of the joules to one side. So that will be 151,080 joules is equal to 24 joules per degree Celsius plus 1676 joules per degree Celsius times the final temperature. So I've moved both of these joules to the other side of the equal sign, and then I've just combined all of my terms that have the final temperature in them. So 24 plus 1676 is 1700 joules per degree Celsius times TF is 151,080 joules. And then I can just divide, so my final temperature is 151,080 divided by 1700 joules per degree Celsius. My joules cancel. 151,080 divided by 1700. The answer that I get is 88.8 degrees Celsius. Notice my unit here is joules divided by joules per degree Celsius. So those cancel. I'm left with 1 over degree Celsius, which is just degree Celsius. So my units do check out. So now, let's evaluate this. Does this answer make sense? Well, first, I would expect the final temperature to be between my two starting temperatures, so 10 degrees Celsius and 90 degrees Celsius. And that's what I find, so that's good. But we want to be a little bit more precise in that. We can be more specific. So the next question is, does it make sense for it to be so close to 90 that it only changed by not even 2 degrees? It barely changed by more than 1 degree. Does it make sense that it's so close to 90? Well, look at the difference in specific heats. So first, there's 4 times more T than silver. So because the mass of the T is 4 times the mass of the silver, and the specific heat of the T is about, let's compare them, 4,200 versus 2,400, it's like 20 times higher. So I'm going to put an approximately here because I did not do that math in my head. But it's about 20 times higher, 20 times the specific heat of the silver. We would expect the silver to have a much larger temperature change than the tea. And that's exactly what we see if the temperature is so close to the initial temperature of the tea. So that is exactly what we found. Also goes without saying that the units worked out. The units worked out to be degrees Celsius. And notice that I showed the units in every step. I didn't just do all of my math and then assume I would get the correct units. You can't just say you have the right units unless you show that those units are consistent with the math that you did. So from all of those, I can say that my answer isn't unreasonable, even if this does seem a little bit suspiciously high to me. But again, with such a large difference in specific heats and such a large difference in the mass, that's not entirely unexpected. So that's how I would go about solving this problem.